This video is about the trigonometric functions of sums and differences of angles. It corresponds to material found in section 7.5 of the textbook. We begin with the sum formula for the cosine function. If we have the cosine of an angle, which is the sum of two angles, here called alpha and beta, we can prove that it equals the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. If we have the cosine of an angle that is the difference of the angles alpha and beta, it equals an expression that is very similar to the one for the cosine of the sum of two angles. The proofs of these equations can be found in the textbook. We can use these formulas to solve many problems. For example, let's say we would like to determine the cosine of 75 degrees. We know that 75 degrees is equal to 45 degrees plus 30 degrees, and that the cosine of 75 degrees is equal to the cosine of 45 plus 30 degrees. We can use the sum formula for the cosine function to find the answer. By substituting 45 degrees in for alpha and 30 degrees for beta. When we do this, we obtain the square root of 2 over 2 times the square root of 3 over 2 minus the square root of 2 over 2 times 1/2, which is equal to 1/4 times the square root of 6 minus the square root of 2. Sum and difference formulas for the sine function are shown here. They are very similar to the corresponding formulas for the cosine function. All four of these formulas are useful, but because they are so similar to each other, they are not easy to memorize. We generally just look them up in tables of commonly used trig functions. Let's use these formulas to establish the identity cosine of alpha minus beta over sine of alpha times sine of beta is equal to the cotangent of alpha times the cotangent of beta plus 1. The numerator of the left side of the equation is the cosine of the difference of two angles, alpha and beta, so we can use the formula for that to substitute in cosine of alpha times sine of beta plus sine of alpha times cosine of beta. We express this as the sum of two terms, and we separate the first term into the product of two ratios. The second term is equal to 1. The cosine of alpha over the sine of alpha is equal to the cotangent of alpha, and the cosine of beta over the sine of beta is equal to the cotangent of beta. And now we have the same expression as the one on the right-hand side in the original form of the equation. The sum and difference formulas for the tangent function are derived in the textbook. We'll just show the results here. These formulas allow us to find the tangent of a wider variety of angles. We can also use them to help establish identities. For example, we'd like to establish that the equation tangent of theta plus pi over 2 is equal to minus the cotangent of theta for all values of theta. Since the expression on the left side is the tangent of the sum of two angles, ordinarily we'd use the sum formula for the tangent function. However, we can't here because we'd need to use the tangent of pi over 2, which is undefined. So we'll use the quotient identity for the tangent. We know that the tangent of an angle is equal to the sine of the angle over the cosine of the angle. We can use the sum formulas for both the sine function and the cosine function. We substitute in 0 for the cosine of pi over 2 and 1 for the sine of pi over 2. And the ratio simplifies to cosine of theta over minus sine of theta, which equals minus the cotangent of theta. Here's another illustration of how sum and difference formulas can be used to simplify expressions. In this example, we want to find the exact value of the sine of the sum of the inverse cosine of 1/2 plus the inverse sine of 3/5. We're trying to find the sine of the sum of two angles. Alpha, which equals the inverse cosine of 1/2, and beta, which equals the inverse sine of 3/5. This means that the cosine of alpha is equal to 1/2, which indicates that alpha is in quadrant 1 or 4. And alpha has to be between 0 and pi, which means it's in quadrant 1 or 2. Well, sine of beta is equal to 3/5, meaning that beta is in either quadrant 1 or 2. And beta must be between minus pi over 2 and pi over 2, either quadrant 1 or 4. So beta is in quadrant 1. We know that alpha is in quadrant 1, so it must be a positive angle. Using the basic Pythagorean trig identity, we can find the sine of alpha. It equals the square root of 1 minus 1/2 squared, which equals the square root of 3/4, and that's the square root of 3 over 2. We use the same identity to get an expression for the cosine of beta, which must also be positive as it's in quadrant 1, and that is the square root of 1 minus 3/5 squared, which is equal to the square root of 16 over 25. And that's equal to 4/5. As we said before, we're trying to find the sine of an angle, which is the sum of the angles alpha and beta. We can use the sum formula for the sine function to find the answer. We substitute in the value for the sine of alpha, cosine of beta, cosine of alpha, and sine of beta. And the result is 4 times the square root of 3 plus 3 all over 10. Let's take a look at another example. Here we want to write the sine of the inverse sine of u plus the inverse cosine of v as an algebraic expression containing u and v, meaning we don't want any trig functions to appear in it. The value of the inverse sine of u is restricted. U has to be between minus 1 and 1 because the sine of any angle is between minus 1 and 1. The inverse cosine of v is similarly restricted, so v is also between minus 1 and 1. We define alpha to be the inverse sine of u. This means, of course, that the sine of alpha is equal to u. And alpha is restricted to being between minus pi over 2 and pi over 2. This means alpha is in either the first or the fourth quadrant. The cosine of any angles in those quadrants is greater than or equal to 0. Now we let beta equal the inverse cosine of v. This means that the cosine of beta is equal to v. And beta has to be between 0 and pi. This means that beta is a first or second quadrant angle. The sine of any angle in those quadrants is not negative, so the sine of beta is greater than or equal to 0. We can use the trig identity sine squared theta plus cosine squared theta is equal to 1 to rewrite cosine alpha and sine beta. Cosine alpha is equal to the square root of 1 minus sine squared of alpha, and sine beta is equal to the square root of 1 minus cosine squared beta. Now we substitute u for sine alpha, yielding the expression cosine alpha is equal to the square root of 1 minus u squared. Then we replace cosine beta with v, and we get the equation sine beta is equal to the square root of 1 minus v squared. Now we can use the sum formula for the sine function as follows. The sine of the inverse sine of u plus the inverse cosine of v equals the sine of alpha plus beta, which equals sine alpha cosine beta plus cosine alpha sine beta. We substitute in u for sine alpha, v for cosine beta, the square root of 1 minus u squared for cosine alpha, and the square root of 1 minus v squared for sine beta. And now we have an algebraic expression that is equal to the trigonometric expression we started with. Let's consider the equation sine of theta plus cosine of theta is equal to 1, where theta lies between 0 and 2 pi. We'd like to know what values of theta make this statement true. First, we square both sides of the equation. Next, we multiply out the left-hand side. Since the sine squared of theta plus cosine squared of theta is equal to 1, We can subtract sine squared theta plus cosine squared theta from the left side and 1 from the right side of this equation. This leaves us with the product 2 sine theta cosine theta is equal to 0, which means that either sine theta equals 0 or cosine theta equals 0. If sine theta equals 0, given that theta must be between 0 and 2 pi, then theta could be either 0 or pi over 2. If, on the other hand, cosine of theta is equal to 0, then given that theta must be between 0 and 2 pi, theta could either be pi or 3 pi over 2. We will test each of these possible solutions one at a time. First, we substitute 0 into the equation. Sine of 0 is equal to 0. The cosine of 0 is equal to 1, so theta equals 0 satisfies the equation. Next, we let theta equal pi, and we get that sine of pi plus cosine of pi is equal to 1. Now the sine of pi is equal to 0, and the cosine of pi is equal to minus 1, so theta equals pi does not satisfy the equation and is not a solution. Next, we let theta equal pi over 2. The sine of pi over 2 is equal to 1, and the cosine of pi over 2 is equal to 0, making the statement true. So theta equals pi over 2 is a solution for this equation. Last, we let theta equal 3 pi over 2. The sine of 3 pi over 2 is equal to minus 1, and the cosine of 3 pi over 2 is equal to 0, which means 3 pi over 2 is not a solution. We see that the solution set for theta is 0 and pi over 2.